Thank you. Now, the shipping forecast issued by the MetOffice on behalf of the Maritime and Coast Guard Agency at 05:05 on Friday the 4th of July. There are warnings of gales in Fitzroy, Shannon, Rockall, Malin and Hebrides. The general synopsis at midnight: Atlantic low 997, moving rather quickly eastwards, expected Faroes 998 by midnight tonight. Low Iberia 1016, slow moving with little change. The area forecast for the next 24 hours: Viking, south or southwest 4 to 6, becoming cyclonic 3 to 5 later. Rain or showers, good, occasionally poor. North at Sierra, south at Sierra, southerly or southwesterly 4 to 6, rain or showers, good, occasionally poor. Forties, Cromarty, Forth, Tyne, Dogger. West 4 to 6, backing southwest 5 to 7, occasional rain, good, occasionally moderate. Fisher, German Bight. West or southwest 4 to 6, showers, rain later, good, occasionally moderate later.
Hi everyone, good morning. Thank you for joining us for this session. My name's Ed Steele. I'm IT Fellow for Data Science at the MetOffice, the UK's National Weather Service. And what you've just listened to is the shipping forecast, the world's oldest and longest running forecast, in this case on the anniversary of its broadcast of its centenary earlier this year. This is a cornerstone of regional maritime safety and a British cultural institution. It's issued by the Met Office on behalf of the Maritime Coast Guard Agency, the MCA, and it's broadcast to mariners 4 times a day via Navtex and via BBC Radio 4 as well. The forecast, as you've just heard an excerpt of, comprises predicted conditions for 31 different sea areas that must be analysed by human meteorologists and condensed into text sentences with a very specific length and format, following a very specific and strict set of rules. So the shipping forecast itself, though, is really a pioneer in the communication of meteorological information, and it can trace its roots back to October 1859, when the steam clipper the Royal Charter foundered in a violent storm off the west coast of the UK. Over 450 lives were lost associated with just this ship alone, and the storm itself went on to claim at least a further 800 lives in total, and 133 ships were lost, with a further 90 badly damaged. The founder of the Met Office, Admiral Robert Fitzroy, as a direct result of this, introduced the first British storm warning service for shipping in February 1861. And in appreciation of the valuable help from the meteorological service by the radio reports that were received from ships, a weather bulletin called Weather Shipping was started, and this became the shipping forecast as we know today. So fast forward to present times, and the Met Office continues to push the boundaries of science and technology, helping people make better decisions to stay safe and thrive by delivering the most trusted weather and climate intelligence in a radically changing world. We're one of the few, if not the only, organisations in the world that crosses a huge diversity of boundaries, covering weather and climate across all timescales, drawing between science and services to both government, industry, across civilian and military, both nationally and internationally, and predicting meteorology and extending this now into hazards. And this all happens in one place. But actually pulling this together, a recent report issued last year from an independent analysis showed that the Met Office is poised to deliver £56 billion of benefit to the UK economy and society over the next 10 years. And this gives a return on investment from the taxpayer in the UK of 19 to 1 on our public money. So a hugely important organisation and service. But what does a 100-year-old forecast have to do with AI? Well, in this talk, Dinesh and I are going to give an introduction to weather forecasting. we're going to talk about the last mile in weather forecasting before proceeding to talk about actually how we architect these solutions to be able to deliver these vital services. We've conducted some unique experiments involving fine-tuning of the Amazon Nova foundation model, which we'll present some initial results from, and talk a bit about some of the evaluation of these so that they can be adopted by other interested groups. So how does the Met Office forecast the weather? Well, it first starts by understanding what the weather is doing now. So we're taking in observations from all over the world. In fact, we're ingesting about 215 billion observations every day that provide the starting conditions for the numerical models that we run to predict how the conditions are going to evolve. This takes place on our supercomputer, where we're computing, using the equations of motion, the evolution of those conditions using mathematical equations to then give us a prediction of what the conditions are going to be. The data from this is provided both directly to some users, but also passed to some of our operational meteorologists who add further value by interpreting some of these complicated fields to be able to distill this information into value-added services for the public. And finally, the accurate weather and climate information is then shared more broadly, benefiting all of the different stakeholders with whom we work, from defence right through to aviation, marine and others. Now, when you step back and think about it, weather forecasting is actually a remarkable achievement. And over the years, we've undergone what's really termed a quiet revolution in terms of our ability to predict the weather. So physics-based numerical models have seen an improvement in accuracy of between about half a day and 1 day per decade. So for example, our forecast in 2013, 5 days ahead, was as accurate as our forecast in 2003, for example, at 4 days ahead lead time. And these improvements have been driven by upgrades to the observations and the assimilation of those data, the dynamics and physical representation of these processes within the maths, and also improvements in model resolution that have been ongoing through this time. And these physics-based models remain an essential component of our forecasting approach. But obviously it's remiss not to mention machine learning and the accompanying AI revolution that we've experienced. Now, the Met Office has always been a big data organisation, and AI and machine learning activities have likewise always been ongoing for many years, although these haven't always been perhaps acknowledged under that specific label. But undeniably, advances in deep learning technologies in particular are really rewriting the rules of entire industries, and including how we predict the weather as well. And what's really brought us to this point are the unprecedented volumes of data, some of which from observations, some of which from numerical predictions, increasing availability of powerful compute capacity, including on services such as AWS, and then also equipping our expert scientists with the data science tools to really be able to exploit these insights and information. And the rise in machine learning weather models has been relatively profound. So what I'm showing here is a graph showing the performance on the y-axis of a particular metric for a data-driven model as a function of the lead time at when it was published. And the key threshold that we're looking at is this blue line, which is the reference level of a physics-based state-of-the-art model. And what we can see is that from September 2017 onwards, we're seeing a steady rise in our ability to predict weather conditions for a subset of parameters using entirely data-driven processes, so involving effectively pattern recognition rather than directly solving the equations of motion. Around this time in the Met Office, we were starting to formulate some of our data science framework. So we were keeping an eye on some of these developments, but also laying out how we would develop our own capabilities in this deep learning space to complement our physics-based approaches, but also how we would work with partners and evolve some of our people to support this. But the world changed when we hit December 2022. And my boss often refers to this as the missing Christmas, because there was a stream of publications of really exciting capability around data-driven approaches in weather prediction that came out literally between about the 20th of December to the sort of Christmas period. And what we can see importantly here is that for the first time for some of these parameters, then we're starting to see the performance of these data-driven approaches exceeding that of our physics-based models. And if we just look at some of the references here, we can also see that these exciting developments were largely driven by some advances from the likes of DeepMind, from the likes of NVIDIA, from the likes of Huawei. So not typical players, but being able to exploit some of these data science capabilities. However, a forecast only actually has value if a user can derive some sort of decision-making benefit from it. And so while we've had this really exciting development in the underpinning opportunities for predicting what the weather will be in different ways, actually there's been remarkably less attention on what the weather is going to do. And arguably this last mile in weather forecasting, a bit like in delivery, is actually potentially even more significant in terms of the opportunities for adding value and adding benefit for our users, because it enables us to provide even more personalized services. It enables us to provide even more multimodal approaches for our data delivery, so that we can have data and accompanying narrative while reducing some of the burden that currently these processes are reliant on human interpretation. So we're super excited about some of this stuff. And to articulate this just with a single product example, so in this case, we're going to use the shipping forecast as an example that you heard at the start. We need to take the complicated data that's output from our weather models and turn this into text at scale. And this isn't necessarily a trivial problem, because these are very large arrays of data that we're dealing with that span multiple dimensions, including both in space and time, but also span multiple parameters. So not only, for example, pressure, as I've shown here, but also we heard things like sea state, visibility, weather, wind speed, wind direction. And all of this has to be framed within the very specific and strict wording and format of the shipping forecast. So this was the use case that we're going to explore in more detail here. Now, just to represent this in terms of some of the technology challenges associated with this, this is really just an example demonstrator of the types of products and services that we're looking to transform using some of these technologies. The reason the shipping forecast was chosen was partly because of its iconic status, but actually because it enables us to test a variety of different aspects and a variety of different data characteristics. So the forecast itself and the underpinning data comprises both atmosphere and ocean model output. So for example, things like wind speeds, but also wave heights. The format of this data is both probabilistic and deterministic, depending on which of those variables from which of the models have been considered. And it is multidimensional. So we're considering that spatial region, so latitude, longitude, and time. And what's particularly exciting about this is really some of the data volumes involved. So considering just the output from a single forecast run from one of our numerical weather prediction models, then we're typically generating upwards of 45 gigabytes of data per individual forecast from the atmospheric models, and about 5 gigabytes of data per individual forecast from our ocean models. When we then consider the shipping forecast. We're able to make some efficiencies, and we're able to crop this down to just the particular variables that we need and particular area that we're considering, that northwest European shelf region. And this results in about 152 megabytes for our atmospheric data and about 7 megabytes for our ocean data. But still fairly large, particularly considering when we're considering fine-tuning foundation models, then this is about sort of 85 gigabytes of data for a 3-month period. An additional challenge from a data science perspective is that some of the formats that we're using here are based on network common data form. So this is largely an atmospheric and an ocean convention. There are very good libraries for being able to read this in, but it's, I guess, not a typical form for that many outside the weather community will necessarily have encountered, but it's quite a convenient form because it's effectively a pandas or X-array type format in memory. So the solution that we were then exploring then was, could we provide this information as output from our weather models and then serve this into a large language model to be able to actually write this text. We were using both a combination of the Amazon Nova Lite and the Nova Pro 1.0 models. 2 hadn't yet come out. And just to frame this task, it usually takes an expert meteorologist a few hours a day to produce this forecast. And in just 4 weeks of prototyping with the team at Amazon, we taught Amazon Nova to do this with between 52 and 62% accuracy in less than 5 minutes. So before I hand over to Dinesh, I was just going to say a few words about the process of how we went about this and some of the background, some of the experiments that we conducted. So we're going to talk about 2 different approaches that we explored, both of which start with taking the weather sensitive data and then that gets run with our models, both deterministic and probabilistic models, to produce outputs. Those outputs are typically, as I say, very large arrays, and those consist of the raw input gridded data. So we're dealing with latitude, longitude, and time in this. And we did, for the large language model implementation, we interpreted these to a text intermediary. So we're extracting statistics corresponding to the different regions of the shipping forecast itself, as you heard at the start, to summarize those and then pass those into the Nova LLM. And this really provides us with a benchmark. What we also explored, and a lot of the focus of our experiments, was around using video capabilities of these types of model. So that same gridded data was first converted and encoded to video, and this was done on a sea area basis typically for most of the parameters, and then we fine-tuned this using the bulletins that had been issued previously by our meteorologists to be able to interpret these as inputs. And then that was hosted to enable us to then run inference on that in real time. But to dive deeper into the architecture of this, I'm going to hand over to Dinesh to talk about that.
Thank you so much, Ed. Hello all, good morning. My name is Dinesh. I'm based out of Luxembourg, and I work with Worldwide SO prototyping team. I work as an applied scientist over there. Before jumping into that, I want to ask a question. How many of you were in replay? Can you raise your hand? Kudos to you. You were able to make the morning session. My manager has to push me out of the replay to come to the session, like have a good night's sleep. Okay, let's dive deep into it now, okay? So I'm going to talk what deployment strategies and what provision we did for fine-tuned model. We'll talk about the architecture deep dive. There are some two main modules. One is large language model, a foundation, and another one is vision language model. And third one, we'll talk about one of the notebook sample where you can actually see the code, especially the machine learning engineer. They want to see how easy it is to fine-tune a model. So let's do that one, okay? So, good. So there are 2 choices or 2 flavors you can fine-tune a Nova model. One is on SageMaker training jobs, and second one is SageMaker Hyperpod. So which one to choose? That depends on use case and also how much data and how long you're going to train the job. For our experiments, our training jobs were running for 3 hours on P548X large GPU, using 4 GPUs. And we didn't want to use the cluster. We wanted to make like quick, dirty runs, like super fast. So we use SageMaker training jobs. But in production, if you have data for like 5 years and you want to train on like several GPUs, several hundred GPUs, and for weeks, so SageMaker Hyperpod is the right tool for you. There is a one small change, like only SageMaker Hyperpod supports PPO. The rest everything is supported by the SageMaker training jobs. As Ed explained, just to recap this one, for large first approach, LLM, how we tackle the forecasting using foundation model. We used 2 LLMs. First one was Cloud Sonnet 3.7, and we compared the output with Nova Pro 1 model. Okay, Nova Pro 1 has better accuracy for this weather forecast, and it was not fine-tuned. It was just doing the simple prompts and process data. So if I show you here, the weather sensor data, it is being picked up over here, the raw input with the grid data. What does it mean, raw input grid data for us? Is you have a multi-dimensional array, and that XY will say like latitude, longitude, and one value will be, maybe one of the weather attribute will have value like amplitude. So you have sea wave height, right? So at certain geographical location, you will see the latitude, longitude, and height of that wave. So that is one of the raw grid data. I'll just give one example, that there are different aspects. So let's stick with that. And that data preparation is done, as Edward mentioned, and we are passing that raw process data to the foundation model. There's one more thing. If in a sea region, there is a sea there is a weather attribute, wind direction. So if in this particular sea region, if 90% of wind is flowing to the north direction and 10% is going northeast, we'll select that entire region as a north direction. So that is the raw data to the data preparation, and that we are passing to the foundation model. Let's dive deep in architecture. So this architecture is built within 4 weeks of prototyping phase. So we have the raw input grid data. It's stored in S3 bucket. As Edward said, it was one run was 45 GB around, but we had a subset of that. And for 3 months of data, it was roughly around 86 GB of numerical data. That's it, 86 GB just for 3 months, and even for subset. That we actually process with ECS because of a parallel processing. If someone is running 86 GB of processing on a single code, it will take like months. These 2 ones is optional, EKS or AWS patch. It is just for telling like data parallel processing can be done choosing one of the 3. Once the data is processed, we are calling the Bedrock Foundation model, and output we are storing into the S3 bucket. Here I want to highlight this architecture is really, really good to process large volume of historic data. Foundation model through the Bedrock mostly supports the batch inference, but you need to check which model supports. The Cloud family supports, Nova family supports. So this saves a lot of time, and it saves a lot of cost as well. There is a one small caveat when you are using fine-tuned model, but I will explain that when we go to the VLM one, okay? Just keep that in your note. This is very flexible because you are using ECS, and under the hood you can use EC2 instance or Fargate based on how much compute power you want to give. And there is one thing in this architecture that is lacking. It is the orchestration is manual. As this was a prototype, we had to do like very quick runs and all. So that's what we proposed this one for the productionize. Okay, and of course for customer to customer it changes. For this use case, we had a S3 bucket here. Sorry, my bad. Yes, I wanted to use the pointer. So for the S3 bucket, we have the data. We have the AWS Glue catalog and AWS Lake Formation. As organization grows, teams want to access the data. And to give the fine granular level access to the data, this data plane will be really helpful for AWS Lake Formation with Glue catalog. Glue catalog is really good if you want to get a subset of data for certain time frame to X to Y, you can run the query and you can get data very easily. We are decoupling this architecture using Amazon SQS. Decoupling is very important in production because what if something goes wrong over here? We need to know, right, which data is failed, which forecast is not being processed. So this SQS is very important. We can attach a data queue also. So if the records is failed, that will be added to the queue, and the team can go deeper into that. Data preprocessing block is same. So ECS, EKS, and batch. You can use any one of these based on your need. Some customers use their workload mostly on EKS, so they prefer to run the processing on EKS, some with ECS. There are other architecture I wanted to just walk through it. What if the use case uses streaming data? So we can use Amazon Kinesis data stream. A Lambda is attached for processing. It depends on how many Lambdas you're going to use. If it's a different processing, one Lambda is output dependent on another, you might use a batch. And once the data is processed, which is formatted for the foundation model, you just call the model. You store the results in DynamoDB table and OpenSearch. Why we are using this? If you want to do the real-time analysis as well. And the last one is serverless event-driven architecture. In this one, everything is serverless. When data is uploaded, once the data is available in S3, it will trigger a Lambda. It will do the processing using AWS step function, and then it will go to the Amazon Bedrock, and data will be stored. Okay, now the second module, VLM. It's much more fun. And VLM, I'm going to tell you the data, how it looks. So every day, there is 4 times the forecast is being generated for 31 C regions. In the first forecast will have 31 C region, and each region will have 5 attributes, 4 or 5 attributes, weather attributes. And for that one, we have to create a video. So we have, and every hour, we are recording we are taking the snapshot of the sensor data. So for 24 hours, we have 24 frames, like it's converted to the raw gridded data to images. So we have 24 images for 1 day of the call, 1 day of the records. And that we are appending after each other, and we are creating 1 second video with 24 frames. That is our input data, okay, for training. And after that, we're going to walk through about the architecture diagram. So this raw input grid data here, it's stored into S3 bucket. That is being processed, the similar logic, data parallel processing. It created from 86 GB of raw gridded data, numerical, to like 56 GBs of video for 3 months of data. And also we had to clean some of the data, so there are some of the incidents where the 2 C regions forecasts were combined. That's how the expert does it. So we have to skip that for training purpose. So that's how in this one we have the raw training bucket data in which we have the training data. Now we use Amazon SageMaker AI to submit a NOAA fine-tuning job. Once the training job is completed, we get the output bucket with model weights. And we are hosting that using Amazon Bedrock. Now I want to talk to you about 2 types of fine-tuning that we experimented. First one is LoRa. What we do in LoRa, we have foundation model, we put the weights like adapter, and we just fine-tune that adapter, right? That's it, nothing else. But when you do a full fine-tuning of a foundation model in which you update the weights of each layer, and that takes longer time also. But it has additional benefit that the model learns more. Here, when you are using LoRa, you can use the on-demand inference. What does it mean, on-demand inference for LoRa? Because the actual model weight is in service bucket, the LoRa adapter weight is in your bucket, in your account, and when we deploy it, that LoRa weights will be appended and the model will be deployed. So you can use on-demand inference. You only pay for how many input tokens and output tokens are generated. However, if you are using full fine-tuning, what's going to happen in full fine-tuning is entire model weights is going to update it. So that model weights is going to be stored somewhere from the original foundation model. And now the new model weights are there, that needs to be hosted 24 hours on instance. So that's why you need to go for provisional throughput. You need to buy the provisional throughput so that you can deploy. So this is a key difference I wanted to highlight. So for this one, when we are using this LoRa, we were able to use on-demand inference. But when we use full fine-tuning, we had to do the provisional throughput. This architecture was built for the prototype, 4 weeks. It is very simple. It lacks a lot of functionality that can be used in the production. So let's go to the production architecture, how it looks. We have different planes, data plane, compute plane, and SageMaker training job plane also. So data plane I want to highlight over here, just bring your attention. So we have Amazon FSx for Lustre here also. So this is added, this is like super fast access. Like if you have a requirement that requires low latency, the FSx cluster, Amazon FSx Lustre can be used for caching purpose. And rest is the similar logic for what we showed in LLM architecture. Compute plane is being decoupled with SQS, and we are doing computing on ECS or EKS or AWS patch. Once the data is being processed, all the videos will be stored over here. So coming back, for one forecast, we have 24 hours of record pass. So we are creating 24 images. We are creating 1 second video out of the 24 images. And we have 31 regions. So we have 31 videos for one weather attribute for 1 day. So this is quite big data, like a large amount of data. We use the SageMaker AI. In this case, you can use SageMaker Hyperpods as well as SageMaker training jobs in production based on the need. Do we really need to go for SageMaker Hyperpod? And then once the model is trained, the weights will be stored into Amazon S3, and then we are deploying it on the Bedrock. Why we are deploying it on Bedrock? The first question comes, what it gives additionally? Because once the model is on Bedrock, almost all the features available for Bedrock, you can use it on that model. You can use the Bedrock Converse API without changing anything. You just need to change the ID of a model, and it works. If you want to use the guardrails, you can use that also. So that gives that undifferentiated heavy lifting over here. There are alternate architecture. I just wanted to walk through it. The first one is model fine-tuning. It's simple. You have data in S3 bucket. Why we are taking everything in S3 bucket? Because it scales really well. And with AKS and ECS, it actually pulls the data pretty cool, like pretty fast. Once the data is there, the data is processed, it stores into the S3 bucket again, and we are using the SageMaker or Hyperpods to train, and we are deploying it on the inference. Second one, how we will be calling that model. Because in VLM, there is a huge amount of data processing. For example, when the data is in S3, this might take at least a minute to process, to create a video. Because the raw graded data needs to be picked up, it needs to be cleaned, then it's converted to the images, and then it goes to the video. So it takes a little bit of time, and once it is done, we will call Amazon Bedrock to get the inference. The easiest way, this part, why not we host it on Amazon SageMaker endpoint? Why you are using Bedrock? Or why we can't host it on Amazon EKS? If you have open source model, like from Hugging Face, a small V3, you can do that one. You can fine tune that model, and you can host it on SageMaker endpoint, or you can host it on Amazon EKS also. We have the LLM and VLM part. Now, how we wanted to show it on UI is real quick. If the application is hosted and accessible to the public internet, we use a CloudFront with API Gateway and AWS Lambda. and decouple architecture with SQS, and it will call the Amazon Bedrock or SageMaker or EKS. The another approach is you put CloudFront, you have the application load balancer, your static website or your EC2 instance website is behind that one. Amazon Container Service. And then through that one, you will call the SageMaker AI or EKS or Bedrock for inference. We have the Amazon App Runner as also Amazon Amplify to host your website. Now let's go into the notebooks. I will ask very difficult question now. Two questions. How many of you has fine-tuned a large language model or any foundation model? Raise hand, don't shy. Okay, now difficult question. Were you able to get it in first attempt to fine-tune? No, cool. That's it. So now I'm telling you, this one, I ran like 25 experiments, and 1 or 2 was failed because I had to stop it because the training data was missed from my side. It runs very smoothly, okay? Now, how the training data looks like. So I just want you to pay attention over here. This system is a system prompt, okay? It says you are an expert in meteorological specialized in UK maritime, okay? This is our user prompt. We said analyze this 1-second video and do this. And this is our input data. This is you say it's Biscay is the sea region, and this is one of the weather attribute. This is our input video, and this is the ground truth or output. That's it. If you have 3,000 examples like this, it creates one JSON-L files with 3,000 lines, and this is getting flattened as one line. So that is our training data. We create training data set as well as the validation data set when you are fine-tuning a model. How you will configure for fine-tuning a model? Like what is this? What is the recipe file? So people who doesn't know the recipe file is just like a configuration for hyperparameters. So in this one, if you see, we give the which model we want to fine-tune. Replicas is on how many GPUs you want to train. We say the training configuration, how many epochs, if there are, you want to control the regularization parameters. Optimizers, there are a bunch of optimizers are available out of the box. You can use it straight away. And this is a LoRa configuration adapter. That's it. And you need this YAML file and a training script. Now let's see how difficult is the training script, okay? For me, it was very hard, but let's see. Cool. It's very simple. Here we define our YAML file, okay? Input data, as I told you, there is a train.json file. For example, I select 3,000 lines JSON file. We have output bucket where we want to store the model weights. Validation S3 URI, validation JSON, okay? I want to pay attention over here a little bit on validation. Whenever you are fine-tuning a model, give validation data set. Why? Because model will try to optimize on a training data set. It will always go the training loss low, but on actual data, it might go up. So you need to find a sweet spot where training data, training loss as well as validation loss is going down. But as soon as validation loss is going up, you need to stop your training, okay? Just keep that in mind. And this one is image URI. This is a Docker image, okay? And it runs very smoothly. There is no issues on the library configuration. It runs as smooth as possible. Then instance types is P548X large. For Nova fine-tuning, you can use P5 and P6 as well. And there is recommendation instance count is 4, 8, and 16. You can add TensorBoard output when you are fine-tuning a model as well. Now we create an estimator. This is just like giving that all the information what was there. And here we get the input, the training input, validation input, and we say fit the model. Within 3 hours, the model will be trained. That was for our data. Now, how to deploy that model? We have here Bedrock client create custom model. So it will create a custom model as in it will get the model weights, okay? And this one create custom deployment means it will deploy on Bedrock. it will take an hour or so to do everything. So I want you to pay attention to the custom deployment ARN. This is kind of model ARN or model ID. Now, how we will get the inference? This is magic codes. So we have the Bedrock Runtime Converse API. We give the model ID. This is a custom deployment ARN. System prompt, which was you are expert in UK meteorology. User prompt, analyze that 1 second video. This is a input video URI, S3 bucket, and that's it. And it will give the output. And this is the ground truth. So it is very close to this one. So here we did a lot of experiments, around 20-25 experiments we did. And we did experiments with the LoRa as well as self fine-tuning, like fine-tuning the entire model. And that's that experimentation and the model, the evaluation will be run by Edward. So I'll hand it over to you. Thank you so much. Thanks, Ed.
Great. Thanks, Dinesh. So having discussed the architecture, we'll just talk briefly about some experiments and evaluations that we conducted to further optimize our particularly presentation of the information to the foundation model. So these experiments in Nova fine-tuning boiled down to 4 things. Firstly, we were looking at combined versus individual models. We were looking at continuous versus categorical data that's provided to these. We were looking at overfitting versus simulation of overstopping. And finally, as Dinesh also mentioned, full rank fine-tuning versus LoRa approaches. Again, just to recap, for our LLM experiments, this was using the Nova Pro model without any fine-tuning. For our VLM approaches, then this was using the Nova Lite model with the fine-tuning as Dinesh has just described. So into some of these experiments then. First of all, we considered how we're formatting these videos. So it's attractive on the face of it to have just a single video that we're providing with all of the information about all of the weather attributes. So clubbing together each of the parameters of interest, so for example, wind speed, wind direction, visibility, weather type, sea state, into a single 5-second video. But actually what we found was that if we're instead breaking these down by individual attributes and training models for each of these, then actually we get a much better result. And the individual models were outperforming a combined model by on average about 27%, because we've got increased opportunity in terms of the prompts that we're providing, increased control in terms of how we're doing this, and there's not so much context switching taking place on that. The next question was actually how we're presenting this meteorological data to the model itself. So typically, we consider, for example, fields of sea state, so our wave height, as effectively a map of how high the waves are, with that height being a numeric representation. But given the specific language of the shipping forecast, we actually have an opportunity to categorize these into the particular bands that correspond to this particular terminology. And again, changing the color scales from just a continuous color scale for the videos that we're provided to these banded categorical values that correspond to the specific terminology of the shipping forecast, again, enabled us to achieve further improvements, with our categorical data models typically outperforming the continuous models by on average about 25.4%. And if you drill a little bit deeper into this, actually the biggest improvements are in areas such as the weather type, where previously just a numeric text label has no real meaning, but actually when we're converting this and labeling this on the y-axis or our color scale on the videos that we're providing, we can provide this additional information to help. What was quite an unintuitive result in many ways was that in our experiments of overfitting versus early stopping, the overfitting outperformed the early stopping despite these having a higher validation loss. And if we trace this back, this is due to a discrepancy between the training objective that we were using in training compared to our evaluation approach. And really the overfitting is enhancing the memorization of precise word patterns, which is specific in the shipping forecast, and therefore produces more confident output. So it increases our word-based F1 scores, giving more accurate and more complete forecasts. But the early stopping, which optimizes this embedded probability or perplexity, fails to capture these types of nuance. And the final experiment that we'll talk about relates to this full rank fine-tuning versus the low rank adaptation. And what we saw was that typically our full rank fine-tuning is outperforming the use of the adapter in these experiments by about 6.2% across our models. As Dinesh explained, the LoRa approach is basically applying an adapter to the pre-trained weights that then enable us to make these adjustments. But it's worth just drilling a little bit deeper into some of the characteristics of these approaches, and particularly some of the cautions in terms of using some of these approaches, particularly compared to a full weight fine-tune. So fundamentally, if the model has to perform only a single narrow task, full model training can still have a performance advantage. We're very closely optimizing it to learn that very specific behavior. In contrast, LoRa will learn less. And I'd refer you to the paper by Dan Biderman et al., which describes this in nice detail. But LoRa learns less, but also it forgets less. So with full model fine-tuning, you can risk catastrophically forgetting the other capabilities that haven't been represented in the training data set. So you can effectively just overwrite this with catastrophic effect if you're not careful. There is, however, compromise in some of this space. And as Dinesh said, we were applying this LoRa adapter just to the final layer of the model. However, there's some recent evidence to suggest that instead of just applying it to that final layer, applying a LoRa adapter to each layer of the network could significantly increase performance, albeit at the cost of increased latency. However, this would provide a more regret-free approach to being able to tune these approaches using LoRa-based methods. And in contrast to the full fine-tuning, if you're also increasing the learning rate as well, could potentially achieve parity of performance in that space as well. It's also worth mentioning, just in the context of some of the announcements this week, that some of the capabilities of Nova Forge as well might offer additional opportunities for being able to comprehensively tune these types of approaches in future. So, having talked a little bit about some of the experiments and some of those optimizations, I think it's also worth touching on the evaluations. And I'd mentioned, for example, some of the F1-based metrics that we'd used, and I'm just going to dive a little bit more deeply into these before presenting the final model comparisons. So throughout our experiments, we used word-based F1 scoring. So as we heard right at the start, the text of the shipping forecast is highly specific and it's structured in its nature, so it doesn't leave much room for creative writing. We therefore wanted to use a direct comparison metric. So we're counting the number of matching words, the number of missing words, the number of extra words between the generated text and the expected text. And I'm showing an example of this just here. So for example, if our expected text relating to the wind characteristics was northeast veering southeast 3 to 5, and our generated text was east or northeast 3 to 5, then we've got 4 true positives, 2 false negatives, 2 false positives in this, giving an overall F1 score of 67%. Now, an alternative approach that other people might have considered might have been using, for example, a BERT score. So this is an alternative to a word-based precision recall, but it provides a much softer match between the words, resulting in an overly lenient impression of performance in applications such as the shipping forecast, where extreme precision is required. So for example, using that same case that I just showed for the word-based F1 score that we used, if this was a BERT-based score, then rather than having a result of 67% accuracy as we were measuring here, you would result in a performance of about 86%, which is a little bit misleading. And really, to drill down into why these types of approaches are so misleading is if we consider, just for example, the word north and south. So obviously, geographical direction is fundamental in communicating where weather systems are coming from. But if we generated an expected word north, and if we had an expected outcome of north and the generated word was south, then actually this would result in a BERT score of 82%, despite this having the complete opposite geographical meaning. And this is because it's working on the embedding level rather than on that word level in the score. So I thought I'd mention that just as a word of caution in terms of evaluating these types of approaches, but also to demonstrate the strictness and the robustness that we applied to these experiments, because we're literally comparing to what the expert meteorologists issued in their bulletins and counting those words on that basis. Now, as Dinesh also mentioned, we considered some comparisons between the Nova Pro model and the Claude 3.7 Sonnet model for the LLM comparisons. And again, as Dinesh mentioned, there was a difference in performance with the Nova Pro scoring an average Word F1 score of 62% to Claude 3.7 Sonnet of 57%, and significantly, from an operational perspective, at a cheaper cost. But I wouldn't drill too much into the actual numbers here, because as we know, within this field, foundation models are being released all the time, and this is only growing. So the main thing to take from this, and as it relates to the architecture that Dinesh talked about at the start, is the great thing about having architected this in Bedrock means that actually, as new models are released, so for example, Claude 4.5 Sonnet, then actually it's just a one-line change within our code to then be able to test this with a new model. And depending on our application, we might find some perform better or worse, but we have this complete flexibility to be able to take advantage of new models as they're released on this basis. It's also worth saying something a bit about the LLM versus the VLM comparisons here. Now, with our LLM-based approach, we were providing information to that through a text intermediary, and we were able to provide a little bit of extra information due to the way we were able to format some of these experiments, and it was on the Nova Pro rather than the Nova Lite model. In comparison, our VLM approach used, for example, a more simple representation of some of our probabilistic information, and this could be significantly improved. But nonetheless, we're getting scores compared to the human meteorologist written bulletins of between 52 and 62%. And the opportunities for evolving this, particularly in the VLM space, is particularly significant. And we think that this is going to be key going forwards in terms of reducing some of the information bottlenecks that would otherwise be associated with providing information to LLMs through a text intermediary stage as well. So just to summarise then some of the key learnings from this. Fundamentally, we've evolved a pattern for architecting scalable AI solutions with considerations of alternatives, advantages and disadvantages that can be applied to this type of data to text conversion that applies to so many of the types of products and services that we deliver at the MetOffice. Also, this provides a framework for rapid experimentation and enhancement. As Dinesh mentioned, all of this work was conducted within a 4-week period, from spinning up the environment to conducting the evaluations and assessments. So just shows the types of velocity that you can work at, both within these, but also with working practices and support from the team at Amazon. Fundamentally, we were looking at comparisons of LLM-based approaches versus VLM-based approaches. And as I said, the LLM performs better because we're able to apply some of the extra domain knowledge that we're able to simplify some of its input. But these textual data descriptions do represent an information bottleneck. So in the future, we're anticipating that the VLM will actually outperform the LLM on this task. And we've got some exciting steps to implement to be able to move forward on this. Finally, we talked in length around some of the fine-tuning experiments that were conducted, and particularly the use of LoRa versus full fine-tuning. So LoRa learns less, so for specialised applications, then actually full model training could have a performance advantage, but it also forgets less, so you reduce the risk of catastrophic failure. And as I said, some of the really emergent research at the moment suggests that applying this to each layer in the model could give a regret-free approach, and there are further considerations and opportunities associated with the Nova Forge framework, which might provide an additional basis for this. I'll leave this up here at the moment, so really just bringing it all together. We've got the full architecture diagram that we used for the prototype on the left-hand side. On the right-hand side, we're just showing some of the interface, and it's recording the interface for the LLM-based approach that provided us a means of being able to expose this to some of our users. And really excitingly, we're moving forward with actually being able to provide some of these outputs for evaluation by our meteorologists, not just applied to the shipping forecast, but applied to similar workflows as well. So really looking forward to this. Just incidentally, what we're seeing here on the left-hand side is we've loaded in the shipping forecast bulletin. This is for evaluation. We're running the LLM task here, and we can see the progress that is associated with this as it's running. In this case, I say it's the LLM task. And then on the right-hand side, we'll start to see the result returned from the LLM corresponding to the shipping forecast that then gives us this opportunity for evaluation on that. So we can see this is now generated on the right-hand side. We can compare this directly to the bulletin that was written by the meteorologists, but we can then also apply our scoring based on these comparisons, so we can actually evaluate the performance of this, which will then feature in the tasks at the bottom down here. So within this same interface, we're just able to start to engage some of those types of interested users on this basis. And then finally at the bottom, we're just generating some of the we're generating opportunities for sort of translation. Obviously, as a National Meteorological Service, then being able to provide data in different or input in different languages is obviously off-the-shelf capability of these types of models, and we can see the output for human reference that was generated there. I'd just like to conclude by thanking you for being here, as Dinesh said. Really appreciate it after replay, but also I'd particularly like to thank the team from the specialist prototyping team from AWS, whose support on this has been absolutely fantastic and absolutely fundamental to unlocking this. So thanking Dinesh, also Emilio and Lewis and Amir, who couldn't be here today, and Kanda, who's the team lead as well. Finally, I'd just like to say, please do provide any feedback on this via the survey in the mobile app. That would be much appreciated. And if anybody wants to chat further afterwards, we'll be at the back and very happy to pick up questions. I can also point you to, on Archive this week, we released a paper describing in more detail some of these experiments that were conducted. So if interested on that, please speak to Dinesh or I, and we'd be pleased to provide that link. Many thanks.
Thank you so much. Thank you.